Hello everyone, my name is Jan Speet. I'm a PhD researcher at Trinity College Dublin, and today I would like to talk about my PhD research titled Wastewater as a Thermal Resource, Exploitation Strategies, Design Methodologies and Prototype Development. The agenda for today will start with a short introduction, after which I'll move on to exploitation strategies, the demonstration sites we developed, and the prototype development. Lastly, I will conclude with a take-home message. I'm sure that nobody will be surprised when I call the disruption of the climate one of the main challenges facing mankind today. To address this challenge, the European Commission introduced the European Green Deal. In the EU, heating and cooling account for around 50% of the total energy consumption, and 75% of heating energy is still delivered by fossil fuels. In addition to this, 15 to 13% of the thermal energy delivered to a building is still embedded in the wastewater when it's leaving the building. That's why in December 2018, the EU officially recognized wastewater as a renewable source of heat. And it's this research that we research in the thesis. We look at three main research questions. The first one is, how can rainwater heat recovery or wastewater heat recovery contribute to the current heating mix? What does this mean for the emission reduction targets and renewable heating targets? We look at the impact of different situations in different sectors on the design of such rainwater heat recovery devices. In other words, how can wastewater heat recovery be implemented? Thirdly, we look at how the set of currently available devices can be complemented or extended with an additional prototype. In short, we look at three different aspects: the exploitation strategy, the design methodology, and the development of a prototype. Researching the exploitation strategies, we looked at three different sectors: the domestic sector, commercial kitchens, and municipal and industrial wastewater treatment plants. The idea in any of these systems is the following. We have a certain amount of energy and water being purchased and consumed by the building. When entering the building, this is distributed over different appliances, and then when leaving the building as wastewater, there's still some value embedded in this wastewater. The idea is to recover this value in the wastewater to reduce the cost, both environmentally and financially, of the building's energy consumption. In a domestic setting, we looked at the wastewater leaving the building with the embedded heat, and the wastewater was then collected in a septic tank or in a wastewater holding reservoir. From this holding reservoir, we recover the heat, and with additional electric work input, it's introduced into a heat pump, which then produces hot water. In case additional heat is needed, an alternative heating source, a peak boiler, is providing this additional heat. The hot water is then stored in a domestic hot water storage tank, from which it is then again consumed by the building. The specificity of this research was that we looked at the temporal aspect of the analysis. We looked at temporal mismatches. This happens in two occurrences, either when supply is lagging demand or when supply is leading demand. And to address this potential mismatch, we looked at different sizes of the domestic hot water storage tank, varying from 0 to 300 liters. In this figure here, we can see that the heating-related greenhouse gas emissions are reduced between 8 and 23% compared to a traditional heating system. However, on the cost side of things, the results are not as promising, since we have a life cycle cost of about 130% higher than the traditional heating system here, represented by the gray line. You can see that over the different sizes of the storage tank, the life cycle cost doesn't vary that much. That's because the capital expenses form the bulk of this life cycle cost, and the savings in operational expenses don't counteract this. So since this was not financially attractive, we decided to move upstream, where there's higher temperature and thus higher heat density. And we looked at heat recovery from commercial kitchens, where the drain or wastewater was led through a heat exchanger, which was used to preheat the incoming fresh water. This reduced the fuel consumption of the traditional heating system, as the temperature of the incoming fresh water was higher. The analysis for the food and hospitality sector in the UK showed a potential of 1.4 terawatt-hour of energy recovery per year, with about 24 terawatt-hour financially profitable. This relates to roughly 350,000 tons of carbon emission savings per year. On the downsides, The currently existing commercial systems have important space constraints. They require a vertical drop of 2 meters. There are some temporal mismatches reducing the amount of heat that can be recovered, and the financial viability is not guaranteed at low flows. Thirdly, we then looked at municipal and industrial wastewater treatment plants. We were moving downstream where we had larger volumes of water but lower temperature. And we developed a spatio-temporal analysis for integrating wastewater heat recovery in district heating, where we used the effluent of the wastewater treatment plant, so clean water, as a heat source for a heat pump, which then delivers its heat to a district heating network. And we applied our analysis on the Tullamore wastewater treatment plant, which you can see here on the black dot. And the spatial component of our analysis showed 5 different zones where the heat demand density was of such a nature that it could justify district heating. Moving on to the temporal side of the analysis, then you can see here the net excess energy over a year for each of the 5 individual zones and for the combination of 5 zones. And you can see here for the 5 individual zones, the net excess energy is positive, meaning that the heat supply is larger than heat demand. But in all these cases, we still have a few days where heat supply is not sufficient to meet demand. On the other side, all zones combined has a negative net excess energy, meaning supply is smaller than demand, but we still have 134 days where supply was sufficient demand. We can also see that even though the net excess energy was negative and the supply was smaller than demand, we still do not exploit the full potential of the total available energy in the wastewater treatment plants. This shows us 2 things. On the one hand, the importance of these spatial temporal mismatches and the importance of the temporal aspect of our research, and then secondly, the need for storage or alternative heating sources. Moving in then to our first demonstration site, which was the kitchen of PENRHYN Castle, tourist attraction, where we let the fresh water into a buffer reservoir from which it was circulated and recirculated to a heat exchanger placed on the drain. When hot water is consumed in the kitchen, the water is then pumped from this buffer reservoir through the alternative heating system to the kitchen. And it's the fuel consumption of this alternative heating system that we wanted to reduce. You can see the kitchen here upstairs, the drain, our 2 heat exchangers installed, and the buffer tank here. After a month of operation, more or less, we saw a reduction of the heat consumption of the kitchen of about 25%, and an additional small part of electric consumption, which is related to the pump's consumption. This would save between 50 and 200 kilograms of carbon per year. The second demonstrator was in the wastewater treatment system of a meat processing factory, where we got the wastewater out from the dissolved air flotation unit into our heat recovery device and then dumped it back into the inlet sump. So we can see here the DAF unit here. The water is let into the top of our wastewater heat recovery device and then let out here back into the sump. Here you can see the pump that leads us to our device in the DAF unit. And here we saw, this week of operation here, a heat recovery power ranging from 8.5 to 10 kilowatt and about 120 to 140 kilowatt hour per day of recovered heat. This preheated the incoming fresh water from 8 to 15 degrees Celsius. Lastly, we then looked at integrating a heat exchanger or a heat recovery device into a grease interceptor. These grease interceptors are already mandatory pieces of equipment in commercial kitchens, and our idea was to reduce space constraints and reduce capital investment in this heat recovery device by combining these 2 systems. We tested our system in the lab with a kitchen simulated here in this hot water reservoir where the temperature is controlled. This hot kitchen wastewater is then led through the grease interceptor with heat exchanger and then recollected down here. And this showed an effectiveness of our heat recovery device ranging from 23 to 55% and a heat exchange power ranging between 600 watt and 1.8 kilowatts. In short, we see 3 ways that wastewater heat recovery can contribute to the future energy landscape. The first one is as an energy efficiency measure, where the incoming freshwater is preheated by the leaving wastewater, increasing the temperature at the inlet of the traditional heating system and reducing the consumption of the traditional heating system. Secondly, something we did not talk about is using it as an energy efficiency boost for heat pumps. The heat pump would be used in a classical way with either a ground loop or an air loop. And after this traditional loop, we would introduce it in a heat exchanger with wastewater. This would boost the temperature of the heat carrier, the example here from 9 to 12 degrees, and thus increase the effectiveness and the coefficient of performance of the heat pump. Thirdly, it can be used as a heat source for heating networks. So this concludes my presentation. Thank you very much for your attention.